Hello everyone. Welcome to the continuation of the last lecture on the topic absolute value function. In the last video, I have already discussed the absolute value function. We defined the absolute value function and we discussed some properties. First six properties were discussed in the last lecture. Alright, so remaining we are going to do it in this lecture. So the next one is the triangle inequality. So we need to prove that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. There are different ways of proving this. So let me pick up one of the ways and prove this quickly. So what I will do is I will look at the term mod a plus mod b the whole square. Let's look at this term and let's expand this using the formula a plus b the whole square. So if I use that formula, this turns out to be a square, that is mod a square plus 2 times ab. So instead of ab, I have mod a and mod b plus mod b the whole square. Right? So this is using the a plus b the whole square formula. Now in one of the properties, I have shown that x square is same as mod x the whole square. So instead of this mod a the whole square, I can put a square by this property. So this turns out to be a square plus 2 times mod a into mod b plus, again using the same property, I can write this as b square. Right? So I have this expression with me. Now we know that for any real number x, x is less than or equal to its modulus and minus x is also less than or equal to its modulus. Again, one of the properties which I have discussed in this list only. So I will use these inequalities here. I know that mod x is bigger than or equal to x. So this expression is going to be bigger than or equal to, I'll be applying those inequalities here. Okay, so and the first and the last part is going to remain the same. So this is a square plus 2 will remain as it is. So 2 times. So mod a is bigger than or equal to a by this property. And similarly, mod b is bigger than or equal to b plus this b square I will drop there as it is. Right? So this expression is going to be bigger than or equal to this expression. And this is nothing but a square plus 2ab plus b square, that is a plus b the whole square. Correct? And x square is same as mod x the whole square. So if you think of this a plus b as your x, I have x square and I can write this further as mod a plus b the whole square. So I started with mod a plus mod b the whole square and we show that it is greater than or equal to this. So finally what I have is mod a plus mod b the whole square is greater than or equal to mod a plus b the whole square. And now by taking positive square roots on both the sides, okay, so taking positive square roots on both the sides, what we have is this quantity is going to be bigger than or equal to absolute value of a plus b. And if I reverse this, I write it in the reverse way. I have modulus of a plus b is less than or equal to modulus of a plus modulus of b. And that proves a triangle inequality. Fine. So this is one of the ways of proving it. Now let's look at another way of proving the same triangle inequality. So we know that for any real number a is less than or equal to mod a and its negative is also less than or equal to its modulus. One of the properties in this list only. And same thing will work for b as well. So I have this with me, right? So I will add these two inequalities first. So that is going to give me a plus b is less than or equal to mod a plus mod b. And if I add these two now, that is going to give me minus a minus b is less than or equal to mod a plus mod b, right? So I can write this expression as minus of a plus b. So a plus b as well as minus of a plus b both are less than or equal to mod a plus mod b. So their maximum is also going to be less than or equal to mod a plus mod b. So maximum of these two numbers, a plus b, and it's negative. So I can write this as, I can take the negative common and I can put it this way. So this will be less than or equal to mod a plus mod b. But what is maximum of x and y? Sorry, x and minus x, that's mod x. And now I have maximum of a plus b and minus of a plus b. So this is mod of a plus b. And that is less than or equal to mod a plus mod b, right? So this is another way of proving the triangle inequality. In fact, there are lots of ways in which you can arrive at this result. So what you can do is each one of you can look out for your own way, to arrive at this triangle inequality, right? So this is triangle inequality. Let's move on to the next property, property number 8. This tells us absolute value of mod a minus mod b. Modulus of mod a minus mod b is less than or equal to modulus of a minus b. So let's prove this. So what I'll do is I'll start with mod a. Alright, so mod a, I can write this as, I can add and subtract b here. So I will subtract b and I will add b. I'm adding and subtracting b, I'm not changing this expression. So if you cancel out b, again you are arriving at this expression, that's mod. So I will consider this as my first term and this as my second term, and I will apply the triangle inequality. So I know that modulus of first term plus second term is less than or equal to modulus of first term plus modulus of the second term, right? So by triangle inequality, this will be less than or equal to modulus of a minus b plus modulus of b. This step is coming by triangle inequality. So finally I have mod a is less than or equal to this. So if I subtract mod b on both the sides, let me write it before. So this is less than or equal to mod a minus b plus mod b. So if I subtract minus mod b on both the sides, or you can transfer this side, this will give us mod a minus mod b is less than or equal to modulus of a minus b, right? So in a similar way, what you can do? Similarly, you can start with modulus of b and you can again add and subtract a here. Similar process. So again, by triangle inequality, if you take this as the first term and this as the second term, this will be less than or equal to mod b minus a plus mod a, right? And we know that absolute value of x is same as absolute value of negative x. Both are same. So this mod b minus a, I can write it as mod a minus b because they mean the same, right? So finally, I have mod b is less than or equal to mod a minus b plus mod a, and if I subtract minus mod a on both the sides, I'll be having mod b minus mod a is less than or equal to modulus of a minus b. And now I will take a negative sign common from here, and that will give me minus mod a minus mod b is less than or equal to modulus of a minus b. I will call this as inequality number 2. Fine. So I have two inequalities, inequality number 1 and inequality number 2 here. Now if you see, if you take this as one term, mod a minus mod b, if you think of this as x, then x is less than or equal to mod a minus b. And if you, that same x is again appearing here, and minus x is also less than or equal to modulus of a minus b. So both of them are less than or equal to modulus of a minus b. So their maximum also will be less than or equal to modulus of a minus b, right? So maximum of mod a minus mod b and minus of mod a minus mod b is less than or equal to modulus of a minus b, and maximum of, if this is your x, then this is your minus x, right? And that is nothing but mod x. That means modulus of this expression. So modulus of mod a minus mod b, and that is less than or equal to modulus of a minus b. And this proves property number 8. All right. So next we have the last property with us. This says if I pick up any two real numbers a and b, then the maximum of a and b can be expressed in this manner: half of a plus b plus modulus of a minus b. All right, so first what we will do is geometrically we will try to understand what this expression says. So let me put it on the number line. So a and b are any two real numbers. So one case could be that both a and as well as b are positive. All right, so both a and b could be positive, and in this I'll assume that b is bigger than a. So let's say b is somewhere here and a is somewhere here. So from here it's clear that maximum of a and b is b, right? So maximum, that is left hand side, maximum of a and b is b. So our left hand side is b. So let's try to analyze the right hand side. So I have a here and b here, so their midpoint will be exactly in between. So I'll put the midpoint somewhere here. This point is nothing but a plus b by 2, their midpoint, right? And if you try to find out this distance, this will be absolute value of a minus b, that is this distance, right? And because this a plus b by 2 is the midpoint of a and b, and this total distance between a and b is modulus of a minus b, so this half distance will be exactly half of this, and the remaining will be again exactly half of this. So this will be mod a minus b by 2, and again this half is going to be mod a minus b by 2, right? And if I look at the distance from 0 to this a plus b by 2, this point, this distance is nothing but a plus b by 2. Actually absolute value of that, but that turns out to be this only. So it's this one, this minus 0, so that will give you a plus b by 2. Now if I try to look at the right hand side, it says half of a plus b first. Actually you can distribute this half to this a plus b and to this modulus of a minus b. So if you give it to half, if you give that half to a plus b, then actually you are covering up this distance. Let me put that in red. So from 0 to a plus b by 2. So that's the first expression, a plus b by 2. So let me put it in red. It is this distance, right? And if you give this half, if you distribute the half to this, half times modulus of a minus b, then I know that this distance which I've marked here, from here to this point, that is actually modulus of a minus b by 2. So again I can add maybe a different color, or maybe with red only I'll do it. So that is this distance. So finally what I'm getting, the right hand expression, it turns out to be distance between 0 and b, and that's exactly b, which was our left hand side, right? So this is what the expression is saying geometrically. I hope that's clear. Now second possibility is that uh, one of them is positive and the other is negative. then what is going to happen in that case? So let's say A is negative and B is positive, right? So again, let me put it on the number line. My 0 is here, A is somewhere on this side because it's negative, and B is somewhere here. Yeah. Okay, so I'll just increase the distance of B so that I can mark the midpoint properly. So supposing this is my real line, 0 is here, A is here, and supposing my B is here. 1 is positive, B is positive, A is negative. So their midpoint will be somewhere here. Let's see, more or less, I'll put it here, right? So now if you see, uh, this entire distance is mod of A minus B. So this distance will be mod A minus B by 2, same, using the same idea as we did in the first case. And this distance again is going to be modulus of A minus B by 2, right? And if you see this distance, that is nothing but A plus B by 2. Now what is the maximum? Again, B is the maximum because B is positive, that's quite clear from here. So B is bigger than A. So if you look at the left hand side here, maximum of A and B, that is B. So our left hand side is B in this case, right? Now let's look at the right hand side. Again, I will distribute the half inside, that will be half of A plus B. And half of A plus B is nothing but A plus B by 2, that distance, and that is actually this, right? Which I have marked in red. And once I distribute the half to the later expression, that is modulus of A minus B, that's modulus of A minus B by 2, which I know is exactly this distance from A plus B by 2 to B, which I have marked here. So this will be again this distance, and this turns out to be the distance between 0 and B, right? So even in this case, geometrically, if you see, this right hand side turns out to be the maximum of A and B, which is B in our case, right? So what you all can do is you all try this thing when both A and B are negative, and you will end up with a similar geometric idea. All right, so geometrically it's quite clear that maximum of A and B is actually this. So what we will now do is try to write it mathematically in a proper way. So A and B are two given real numbers to me. So without loss of generality, I'll assume one of them is bigger than the other. All right, so I'll assume that B is greater than A. So because B is greater than A, if you want to put it, so B is here and A is here somewhere on the number line. Now because B is greater than A, what will be maximum of A and B? This set is having only two elements, A and B. And because B is bigger than A, maximum of this set is going to be B, right? Now on the other side, I have half of A plus B plus modulus of A minus B. Now because B is greater than A, what will be absolute value of A minus B? So since B is greater than A minus B will be negative, right? A minus B is negative, and because A minus B is negative, its absolute value will be its negative, and that is nothing but B minus A, correct? So modulus of A minus B is nothing but B minus A in this case. So finally what I'll have is this will imply modulus of A minus B is going to be by 2 is going to be equal to B minus A by 2. Now if I look at the right hand side expression that's here, if I look at the right hand side expression, what is the right hand side? Right hand side is half of A plus B plus modulus of A minus B. So if you distribute the half, you get half of A plus B plus half of modulus of a minus b, right? But modulus of a minus b by 2, this entire thing is b minus a by 2 from the previous expression. So this will turn out to be a by 2 plus b by 2, that is the first expression here, plus this is b minus a by 2. So b by 2 minus a by 2. So a by 2 will cancel out with this a by 2 and you are left with, sorry, this is 2. B by 2 plus b by 2, that's b. And b from here is nothing but maximum of a and b. So we conclude that maximum of a and b is nothing but half of a plus b plus absolute value of a minus b, right? So we have proved property 9 as well. Now the homework for y'all is we have a similar expression for minimum also. Okay, so what y'all can do is y'all prove that minimum of a and b is nothing but half of a plus b minus absolute value of a minus b by 2. A by 2 is, I've taken it common. So this is what you have. So what you do is you'll try to look at it geometrically in this manner and try to prove it rigorously this way. All right. So I will leave this as an exercise. Next, we have a definition of a bounded set. We had already seen this definition when we spoke about bounded above and bounded below sets. But I want to give this expression in terms of absolute value. So we will just recall the definition of a bounded set, right? So a subset A of R is said to be bounded in R if and only if that set A is bounded above as well as below. So I will call a set to be a bounded set in R only when it is bounded above as well as below. So when do you say that a set is bounded above and bounded below? It should have a upper bound and it should have a lower bound respectively, right? So that is a subset A of R is bounded in R if and only if, I can rewrite this as there exists a upper bound and a lower bound. So there exist real numbers alpha and beta such that alpha is less than or equal to x and x is less than or equal to beta for every real number x. That means x is less than or equal to beta for every x in A, sorry, not R. That means beta is the upper bound for the set A and hence the set A is bounded above, and alpha is less than or equal to x for every x in A. That means alpha acts like a lower bound for the set A and hence the set A is bounded below. Fine. Now for example, if I look at this interval, let's say my A is minus 1 comma 4 say. So let me plot this on the number line. Approximately it must be somewhere here. 0 is here, minus 1 is here, and let's say 4 is here. So this is my closed interval minus 1 to 4, which is a set A. Alright. Now this set A is bounded in R. Why is that? Because I can see that minus 1 is a lower bound. Minus 1 is less than or equal to x for every x in A, and every element is less than or equal to 4. And this is happening for every set, every point x in the set E. That means the set A is having a lower bound and an upper bound, and hence it is a bounded set, right? So A is a bounded set in R. Now what I'll do is this lower bound and upper bound we will try to analyze these upper bounds and the lower bounds. If -1 is a lower bound, then anything less than -1 is also a lower bound. This is what we had discussed in our lectures before. And if 4 is an upper bound, then anything bigger than 4 is also an upper bound. So what I'll do is, I will take the absolute value of lower bound and the upper bound here. I'll look at -1, its modulus, and modulus of 4, and I will look at the maximum of these two elements. Mod -1 is nothing but 1, and mod 4 is 4, and the maximum is 4, right? Now what I'll do, instead I'll pick up the maximum first, 4. So 4 I have here, that I'll keep as it is. Now this, instead of -1, I can also pick up -4 as the lower bound of the set A, right? Also -4 is less than or equal to x, and x is less than or equal to 4 for every point x in the set A, because -4 is a lower bound again, and 4 is my upper bound. So, and one of the properties which we have discussed in this in the previous video, it is of the form, this is of the form, minus a is less than or equal to x, and x is less than or equal to a. And this is true if and only if absolute value of x is less than or equal to a. So I can write this condition is, this is if and only if absolute value of x is less than or equal to 4 for every x in a, and this condition takes care of both the upper bound as well as the lower bound. So instead of writing two numbers -1 and 4, this will do the job for me. So what I have to do, I have to look at the maximum of modulus of this lower bound -1 and modulus of this 4, and this 4 will be bigger than absolute value of every element in the set A, right? So this idea we will capture in the coming proposition, which says a subset A of R is bounded in R if and only if I can find one real number m positive such that -m is less than or equal to x, less than or equal to m for every x in A. And this condition is actually equivalent to this: mod x is less than or equal to m for every x in E. All right. So you can compare this idea with the upcoming proposition. So that's an if and only if statement. So there are two sides for it, and we have to prove both the sides. So first I'll assume that A is bounded. Supposing A is bounded in R, right? So what we have to prove? We have to prove that there exists a positive real number m such that mod x is less than or equal to m. Once we do this, one side will be done. So because A is bounded in R, it will have a upper bound and a lower bound. So there exists real numbers alpha and beta such that these conditions happen. This is by the previous definition of a bounded set, which I said in the previous slide. All right. So what we do then, we look at the absolute value of A and the absolute value of B, and we pick up their maximum. So I will choose my capital M to be maximum of absolute value of alpha and absolute value of beta, right? So choose this as M. This is what we had done in the previous example. And now what we have to do is, we have to show that modulus of x is less than or equal to this real number m, right? So we have to estimate mod x for every x in A. We have to show that it is less than or equal to capital A. So now one thing we know is mod x, I can express it as maximum of x and minus x. So if I want to estimate mod x, it is as good as estimating both these numbers, x and minus x, because mod x can take one of these numbers, either x or minus x, right? Now it's already given to us that x lies between alpha and beta for every x in A, right? So note that uh, alpha is less than or equal to x and x is less than or equal to beta, and if I multiply a negative 1 to this, the inequalities will be reversed and I'll have this expression. So these two are true for every point x in A, right? Now mod x has two choices, either x or minus x. So we will consider both these cases. If mod x is equal to x, then what is going to happen? And if mod x is equal to minus x, then what is going to happen? So if mod x is equal to minus x. So these two cases will do the job for us. Alright. Now if mod x is equal to x, then I have mod x is equal to x. But what I know about x from the previous slide, x is less than or equal to beta. That's here. So x is less than or equal to beta. And we know that every real number beta is less than or equal to its modulus. So beta is less than or equal to mod beta. And what is capital M? It's the maximum of mod alpha and mod beta. So this will tell us that mod alpha is less than or equal to M and mod beta is also less than or equal to M, because M is the maximum, right? So this mod beta is less than or equal to M. That means mod x is less than or equal to M. So in the first case we are done, right? Now if mod x is equal to minus x, then what do we have? Mod x is equal to minus x, but what I know about minus x? From here, minus x is less than or equal to minus alpha, the last expression here. So minus x is less than or equal to minus alpha, and minus alpha is always less than or equal to its modulus. Any real number is less than or equal to its modulus, and mod alpha is also less than or equal to M. So I have this to be less than or equal to capital M, right? Cases we showed that mod x is less than or equal to M. That means we are able to find one real number M. M is positive, okay? M positive, such that mod x is less than or equal to M for every real number x in E, right? So we proved one side. Now we have to look out for the second, reverse, converse. So let's do that. So conversely, the second part, I'll assume that there exists a positive real number M such that mod x is less than or equal to M for every x in A, and we have to show that the set A is bounded according to the definition. So because mod M is less than or equal to M, this implies minus M is less than or equal to X, and that is less than or equal to M for every X in A, because one of the properties is telling us that these two statements are equivalent. This implies minus M is a lower bound for the set A and capital M is the upper bound for the set A, and therefore the set A is bounded in R because it is bounded above as well as bounded below. So this is a trivial case. The second case is a trivial one. The first case you have to work a little. All right. So a set A is said to be bounded in R if and only if you can find one positive real number M such that mod x is less than or equal to M. and at many places we will be using this definition instead of the previous definition which I stated. All right, so we will prefer this proposition over the previous definition. Fine, and these are my references. Thank you.